Hello again to all my friends. This is Systems in Action 6. Sixth video, and we're dealing with efficiency. My star is not efficient because I have to go over it 100 times to make it look like a star. What do you think?
It's beautiful.
It's beautiful, thank you. That was Mrs. Podlipsky, but I am Mr. Benjamin. Mr. Benjamin. Ha 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 ha.
And I don't have my own stylus, so now I have to take yours.
Well, at least I'm offering it to you. It's not
That's
like
true.
that silly Mrs. Terrio, who's probably going to be
steals.
listening to this.
She steals them.
Hello, Mrs. Terrio, and everyone else. Anyways, we were looking for a joke to introduce this video, and we can't find one.
Because systems are serious things.
They're very serious. You can't, efficiency, come on. That's very serious. So I remembered the riddle that we talked about. I'm not going to give you the answer, but I am going to read it out to you. I go up, I go down, to the sky, sky's in blue, and to the ground. Present and past tense too. Let's go for a ride, just me and you. ... Think about what that is. We'll maybe put it in the try this or something afterwards, I don't know. But our learning goals for this video is to calculate the efficiency of a machine, and there's a formula associated with that, and we will talk about that. We also want to describe useful output and identify ways to increase efficiency, and there really isn't any formulas for that, but we're going to talk about it anyways. So efficiency is a measure of the useful work done by a machine. We don't really care about the other work done by the machine. We want to know why it's good for us. And we compare that to the work needed to operate it. Now we're going to consider the effort and the load. The effort is all the work we put into it. That's why it's known as effort. And the load is what you get out of it. And this isn't going to fit. But like I said, effort is what you, or load is what you get out.
So effort is your input force, load is your output force. If you get confused about those terms and which ones to use, one thing that you can remember is if you're thinking like alphabetically, E and I are closer together, so effort and input, and then load and output are further down the alphabet, so they're kind of together. So that's just kind of a little
E-I-L-O.
Little trick to help you out.
E-I-N-G-O. No, anyways.
Okay, so when we're talking about the useful output, this is the work that a machine is actually designed to do. So if you look at Mr. Benjamin drew you a beautiful bicycle here.
That's what my bicycle looks like at home. That's why I drive my car.
No, your car is probably going to get you further with less work involved. I'm just going to put.
I don't even have any spokes. Isn't that sad?
Yeah. I wonder, do people still put like cards in their spokes?
I don't think they do.
Then it makes like little noises. Anyways, so if we're thinking about a bicycle, what would you say is the useful work? What do you want out of a bicycle, Mr. Benjamin?
Forward motion.
That's right. You want to move forward. So if you need to get somewhere, you want to make sure that your bicycle is rolling in the correct direction. And in order to do that, you've got your little, let's put like a little mechanism here. So you've got those pedals that you're going to have to crank. And so as you put force onto the pedals, it moves the bike in the correct direction. So
the effort you put into it are your
legs. The effort
legs.
you put into it. So the effort is your input force, and the output force is the load. So it's moving in the correct direction.
Phone call. Sorry.
That's Mr. Benjamin's phone ringing. So when you're moving in a forward direction, that is the work. That's your useful output. That's the work that you want that machine to do. But sometimes you end up losing some of that efficiency. I'm going to back up here for a second. So if you're losing some of that work and it becomes not useful work, there's some reasons for that, and you guys probably will come up with a list on your own. But some of those things that would cause you to lose some of that energy and not have it going into your useful output would be something like friction.
I think we have a slide on that afterwards.
Do we? Okay.
Yeah, but oh well, we can talk about it here.
And that's the big one. So friction and even heat. And we've talked about that a little bit. Okay, so what are some things that make a bike more efficient? So if you think of, there's different designs of bikes. One would be like a mountain bike versus a road bike. So some things that change those would be, I'm just going to switch to a different color here.
Purple's too dark.
There we go. Would be the tires. So if you think of a mountain bikes have a lot of tread on them, and
they're
so if you're
thick and chunky.
they're thick and chunky. They're so that they can actually they want friction because you want to be able to grip onto the terrain inside of a forest, for example. But if you were to take a mountain bike on the road, you're going to also grip the road, and you're going to lose a lot of that efficiency with friction. So the tires are a big one. Another one might be the weight of the bike. So you might have the weight.
Sorry.
It's okay. So we're talking about perhaps the frame would be a little bit different in weight. I actually have a picture here.
It could be different material. It could be thinner. It could be thicker. The frame could be structured in different ways. So a lot of different reasons why the weight could be changed.
There we go. So here's an example of a whole bunch of different tires. So depending on which one you have, you're going to have different amounts of friction. They're going to be put against the substrate or the terrain. So for example, downhill, that one's going to have lots of friction, whereas your road bike, this one here, will have less friction so that you get more efficiency and it's easier to pedal. So things that make your bike more efficient, well, it depends on what goal you have. So if you're thinking about a road bike and you want to go further with less resistance, then we're talking probably about something like this instead of this.
Thinner
right?
tires.
We don't want that. Thinner tires that have less contact with the ground, less tread, a lightweight bike that's going to allow you to move faster so you're not having to pedal the weight of the bike. The other thing is changing gears. Mm-hmm. Right, so if you change gears...
We're getting kind of mechanical.
Yeah, then you actually are changing the efficiency of the function of the bike itself. Something else you might think of are foot straps. Right? So that as you pedal, you're not just putting force downwards, but actually when you're bringing your foot back up, then it's adding some of that force.
So we've taken this bike and made it much more efficient. Keep that in mind for later. Okay. Where does this energy go? I'm probably going to erase this part, but anyways. Ignore that. I actually don't even know what that said. Let's find out what it said. How to increase efficiency, new bulbs. Oh, okay, never mind. So where does all this energy go? This Podlipsky actually touched on this really quickly, but it's mostly lost to heat and friction. If you look at this excellently drawn light bulb by myself here, this is an incandescent light bulb. So,
how can you tell?
Because it's shaped like one.
And it's got a filament in it.
Yeah, it's got a filament. It's got some tungsten in there. But anyways, this light bulb is around 90% heat. If you plug this light into the screws inside of your walls and outlets or whatever you want to call them, you are going to take that energy and create 90% heat and only around 10% light. That looks horrible. That should probably be in yellow. Or you know what, white's fine. And only 10% light. Meaning this really isn't efficient. The ways we can change this is by using different bulbs. So LED lights are much less hotter.
Less hotter?
Less hot?
Less hot.
Does that not make sense? There's
less
less heat.
Yes.
Less hot.
So
and you get
efficient.
better light, more efficient.
Same with fluorescent bulbs.
Mm-hmm.
LED is light emitting diode.
Diode. And you know those OLEDs, those are organic.
Oh.
I don't know how that works, but they're
Don't know.
organic. This is a good looking light bulb though, isn't it?
It's beautiful.
It's
Not efficient, but it's beautiful. Actually,
Look
it
at all
should
those
be, you should have them going like this.
Yeah, the heat's
'Cause
emitting,
it's heat
right?
coming off of it rather than light.
Look at that. That'll make a good
It's
thumbnail.
hairy.
Hopefully that comes out to the thumbnail. If we want to calculate our efficiency, we're going to use a formula. I'm going to erase all this, but don't worry, we can get it back. At least I hope so.
Well, when you're talking about percentage, I mean, these guys have calculated percentages on tests and that sort of thing. It's basically kind of the same thing. You're going to take some sort of ratio and then times it by 100 so that you can get a percentage out of it. So in this case, when you're talking about efficiency, we're talking about useful output of work, so that's in joules, divided by the input work in joules. So how much of the total input is going to be actually produced as useful work?
And this value is multiplied by 100 to get your percent.
That's right. So it's not measured in joules. The efficiency is actually going to be measured as a percentage. So your final unit is percent, because those joules will cancel out.
That probably looks really weird on the video, getting rid of all that. Oh, jeez. Now I just erased something. I don't know what I erased, but oh, it looks pretty good here. Things we want to keep in mind. Sometimes you will be asked about load and efforts. The way Ms. Podlipsky told us to remember it is, think about the alphabet. E is very close to I, so that gives you your load or your effort and input, and L is closer to O. A, B, C, D, E, F, G, H, I,
So those
E and
are
I,
together.
and then L, M, N, O, P. There you go. and this is L/O. So these work out together. So efficiency can either be equal to useful output, which is your work in joules, divided by your input work, also in joules, or your load divided by your effort, all multiplied by 100. Sounds a little confusing, but it's really easy. Let's do a quick example. Let's get some numbers in here as well.
Okay, let me read you an example, and you can write down the given information.
Mm-hmm.
So, for example, a machine is capable of doing 35 joules of work. When 50 joules of work is put into the machine, what is the efficiency of the machine?
So if 50 joules was put into it, this is our
That's your input.
effort or input.
And it's capable of doing 35 joules of work. So
And this
that's
is our output.
Yeah, that's the useful output that you're given from that machine.
And the reason why we know that is the machine does this. Oh, we're already at 10 minutes. We gotta hurry up.
We're not being efficient.
We're not being efficient. This is horrible. What's required? Efficiency.
So
And this is in percent.
Notice Mr. Benjamin is writing his grasp.
That's right. That's how we answer our questions.
That's right.
Analysis. We are going to use E equals input.
Nope,
Output. Sorry. Mistake. Output over input times 100. Or it would be effort. Nope. Load. There you go. Load over effort. I'm going to go to the... Well, I can't go to the next page, can I?
Just erase it.
Yeah, I'll just erase it and write it afterwards. Our solution. So what numbers we had? We had E equals 35 joules
Divided by 50.
over 50 joules. And this should be 70-ish? Yeah. 50 times 2 is 100. Yeah, equals 70. And we'll multiply that by 100 to give us 70%.
And then you paraphrase, but we don't have room for that. So when you guys answer these questions, make sure that you answer in a
We can
complete
verbally
sentence.
paraphrase it and say that machine has an efficiency of 70%.
Perfect.
Try this.
Yeah, let's give them a task.
We want you to think of a machine. It can be a simple machine, it can be a complex machine. Any sort of machine except for a bike, because we've already done a bike. And tell us how you, as an individual, can make it more efficient.
Or even how, I guess, society has
Society
made
in general, yeah.
Yeah.
Any individual who would want to do
Yeah,
that.
so don't use bike and don't use a light bulb because we've talked about those two things. But give us some sort of machine and how we've come up with solutions or solutions you can suggest to make that machine more efficient.
Ha 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 ha. Square face. Anyways, then we're going to say thank you.
And good luck.
Thank you.
We'll talk more about it in class.
Bye-bye.
Bye.